Welcome back. This is lecture 30. So we were discussing impedance transformation network, or rather, to be more specific, we are seeing ways of transforming one impedance into another without using an explicit transformer. We were trying to use typical L's and C's to take one resistor of certain value to a different value, and preferably higher value, right? Again, what was the modus operandi? So we were essentially, just like in a transformer, I know that the power on the both sides of the port are the same. So if you have a lossless network and you inject some power on one port, which essentially means that if something is some resistive network is connected to the other port, the power in has to be equal to power out, right? So using that principle, all we said is if the voltage at the secondary port gets stepped down, which essentially means that it will get, the effective resistance will get up converted in the primary port, right? So that's essentially was the way of working. And the architectures that we had, we looked at a couple of architectures, but typically the architectures were of this order, of this form. That is, if we have some Z and if we have some R, then I know there will be a voltage drop across Z and a part of the voltage drop across R, and the rest of the voltage will drop across R. And if this voltage drop is significant, right, then I get a lot of step down of the voltage. And if I do that and I put in another impedance Z prime, such that the imaginary part of this impedance, right, gets resonated out with Z prime, right, then we get so what we are saying is, at some omega naught we get a transformation ratio N, which is equivalent to the step down voltage, which is effectively the ratio of the step down voltages. And if I neglect that plus one term and all, this N is approximately equal to Z by R. So basically 1 over R by Z, right? 1 over R by mod Z, right? So that typically is the transformation ratio. So, and then second step is, if you resonate out, this is Z in, imaginary part of Z in with Z prime, right? Then Z transformed, not Z transform as in digital signal processing, but the impedance transform. So rather, I would say that Z, let me just call this port 1, port 2 just to remove the hassle. So let's say Z 1 1 1 1, so Z 1 1 1 1 prime will be equal to N squared times R, right, if the above two conditions are satisfied, right? So by the way, here the assumption is N is much greater than 1, right? Otherwise you have to do a brute force analysis, and those plus 1 and all those terms are going to come into picture. But we saw a couple of architectures of this format where Z was replaced by an inductor or a capacitor, and then we saw how to resonate these things out. One aspect to those architectures was the fact that in certain architecture we saw that, I mean, in this case the N was always a function of the frequency, right? For example, if Z is an inductor, this N effectively will be omega naught L by R. If Z is a capacitor, then this N is essentially omega naught CR and so on, right? So the key thing to note is that, or rather 1 over omega naught CR. So but the key thing to note is that both these cases N is a function of frequency, and not only that, the constraint of N much greater than 1 will impose another constraint, that you are going to either be able to use this particular network at a frequency higher than some value or a lower than some value, right? Simply because this constraint of n greater than 1 will appear only if that you have a lot of voltage drop across Z and lesser across R, right? Let's say we do not want this constraint, we do not strictly want this constraint to limit us. Okay, so in principle there will always be some limit, but let's say we do not want that ratio, right? If I have to rephrase, let me say it this way: if I do not want that transformation ratio to be tied to the frequency of interest, because it is quite possible that I want that transformation at a certain frequency where resonant frequency is something else, right? So in that case, obviously I have to look for some sort of impedance divider which is independent of omega. I mean, you might say that we can always put another resistive divider, but we don't want to do that because any resistive divider will cause another additional loss, and the whole purpose of doing all these things is because we do not want any loss. Basically, we want an ideal transformer kind of scenario, right? So what are the other options? If resistive divider is not allowed, I can do an inductive divider, I can do a capacitive divider. Fine, so let's do a capacitive divider. So let's say I have, this is the input port, and I have a R, and I want this voltage applied, whatever I am applying at the input port, a fraction of it to drop across R, to appear across R, and we are proposing to do it by dividing it using a capacitive divider, right? So let's do a capacitive divider, simple capacitive divider. Let's call this C1, this C2, and if I connect these two, right? If I connect these two, what do I get? What is this voltage V0? Now obviously I can, for the time being, let's also make it a 3 terminal. So let's connect these two also. So now obviously I can work it out how much, this is a simple circuit, I can work it out what will be V0 with this division ratio. But note that there are certain constraints that I want this to have, right? I want this division ratio, this voltage division between V0 and V11 to be independent of any omega, which means that I want basically the capacitor ratio to dominate, right? So if that is what we want, right? So what do you want? We want this n to be equal to 1 over this division ratio, that is C1 by C1 plus C2, right? So basically 1 plus C2 over C1, right? Okay, so this is what we want ultimately, right? So now note that moment I introduce R, strictly speaking, this division ratio is not that. But next question is, under what condition the division ratio will be this? So the condition in which the division ratio will be this is another condition when the impedance looking here, right? The impedance looking here at whatever frequency of interest is much smaller than R. You do not want the R to load the capacitive divider. If R loads significantly the capacitive divider, some current is going to get diverted to R, and essentially if a significant fraction of the current gets diverted to R, then the amount of current that flows into C2 is going to reduce, and hence that division ratio will also be a function of R. And moment the division ratio becomes a function of R, the omega will also come, because the omega exists in the C1 and C2, right? So you do not want loading. So under what condition there will not be loading? The condition in which there will not be loading is the Thevenin impedance looking into inside that network, the one that I have shown, right? So this Z Thevenin, this has to be much lower than R, right? Or rather, mod of Z Thevenin has to be much lower than R, right? So what this to happen, you have to ensure that mod of Z Thevenin is much lesser than R. So basically no loading condition. So for this to happen, what should I do? We need to find out the Thevenin equivalent. How do I find out the Thevenin equivalent? So you kind of short this, right, and find out the effective impedance into the port, looking into that terminal. So which means that I am interested in this part, right? So what is ZTH? So clearly the ZTH is a parallel combination of C1 and C2. So ZTH becomes 1 by J omega C1 plus C2. All you want to ensure is that 1 by omega C1 plus C2 is much less than R, or in other words, this is going to operate at frequencies where omega is much greater than R times C1 plus C2, right? So as long as this is satisfied, your division ratio is independent of omega, correct? So if that condition is satisfied, then we know the division ratio is independent of omega, so that's good. So we have one problem that is solved. So let's assume that problem is solved, because normally we would like to operate at, in most cases we would like to operate in RF, we would like to operate at higher frequency than some threshold, right? So if that going to higher frequency is always a more troublesome thing, and using and the previous architectures that we saw in the last lecture, if you use a capacitor, then it appears to be that we have to operate below a certain frequency. But it looks like using this architecture, you can kind of this encourages operation above a certain frequency. So that's good, right? And why capacitor? Why am I interested more in capacitor? If you are operating at some lower gigahertz frequencies, the capacitors are more ideal and they take up less space than an inductor. Hence the interest, right? So that's good. So let's come back here. So when we are essentially saying that the R is not loading the capacitive divider, what is the effective imaginary part, or rather what is the effective impedance approximately that you are going to see from here? Obviously you are going to see a real part, and what will be that real part? That real part will essentially be n squared times R, correct? But you are also going to see an imaginary part, right? But what will that imaginary part be? And it is easy to visualize in this case, because if the capacitor divider is, if the R is not loading, then almost the entire current is flowing through. Almost the entire current will flow through C1 and C2, and a part of it, a minute fraction of it, is going to flow through R. And because lesser amount of current is flowing through R, we are basically getting that up conversion, right? So that's the, you are getting lesser voltage and hence the up conversion, right, of the resistance. So that all checks out. So which essentially means that the effective impedance that you are, or the imaginary part of the impedance that you are going to see, is essentially series combination of C1 and C2, and that will come here, right? So you are going to see an effective C equivalent, which is approximately equal to C1 C2 by C1 plus C2. And now if you want to resonate C equivalent out, what are you going to do? You are going to put a inductor around this port, which is 1 prime, which means you are going to put an inductor here, such that at omega naught, your L omega naught square is 1 by L times C equivalent. Then you would naturally see an upconverted impedance between 1 and 1 prime. Similarly, you can play the same game, and you can use inductors if you want. In fact, if you go to millimeter wave frequencies and all, then sometimes the inductors might be more useful to be used as a divider. So I call this L1, L2. So, and then you use a capacitor here to resonate it out, and in this case your N is effectively L1 plus L2 by L2, that is 1 plus L1 by L2, right? You ensure that this is much greater than 1, right? So you have to ensure that this is might not by default, but it's 1 point, it cannot be like 1.2, right? So it has to be like 3, 4 or something like that. If that is the case, then that N squared R becomes multiple times of R, and hence you get kind of good enough up conversion, right? Okay, fine. So this is as far as stepping the voltage, stepping the resistance up is concerned, right? But what about in certain cases we would like to step the resistance down also? When we will be discussing about power amplifiers, you will see that there will be a real need to step the resistance down to a certain value, right? From 50 ohm or so, right? So how should I go about thinking about it? the argument remains the same. So in principle, what did we do to get the resistance up? We applied certain voltage at a port, right? We applied a voltage here, and this is lossless. We said that if I apply a voltage here, and this becomes V by N, then the resistance here becomes N squared R, right? But if I want to flip that argument and say that I want to increase, or rather I want to decrease the value of resistance, then what should I do? Then one might say I need to increase the value of voltage at the other terminal. Yes, that would definitely suffice, because this is a lossless. If I increase the voltage, it suffices. But visualizing increasing voltage is probably not that straightforward. But we can do something else, right? What can we do? Instead of increase, ultimately is V times I, correct? V times I is constant in both ports. If increasing, the way I like to visualize it, if increasing a voltage is probably not easy to visualize, then maybe decreasing a current is easy to visualize, right? So that's what I mean. That's the way I like to think. So let's see if I can decrease the current, right? So again, you have an R, you have a current source. You don't, if you connect it directly, all the current flows into the R. But I want a fraction of this current to flow in. So if I do that, what should I see? So let's say if I do the same thing, right? So let me first argue this, then I will get there. So let's say this is I in, and I say that the current that is coming out, how I don't know, the current that is coming out is I in over N, right? So what is the voltage? The voltage is obviously I in over N times R. So what is P out? P out is R times I in over N times I in over N. So this has to be equal to P in, right? What is P in? P in is I in times this voltage across V11 dash, correct? Right? So this is equal to R times I in squared by N squared, which means that your V11 prime by I in becomes R by N squared, correct? So the trick is to ensure that come up with architectures which divides the current by a certain fraction. So how can I come up with such an architecture? I mean, once you know what to do, then it's very easy to do. So all I have to do is divert the current out, and I do not want to divert the current using resistors. What other options do I have? Capacitors and inductors. So use a capacitor. So I use a capacitor to divert the current out. So what is the division ratio? If this is I in, what is IR as a fraction of I in? So this is basically I in times 1 by j omega c by R plus 1 by j omega c, right? So this is I in times 1 by 1 plus j omega r c. But if I want this division ratio to be much greater than 1, so now obviously I want that if omega rc is much greater than 1, then your IR, at least the mod of IR, becomes I in by omega rc. So this guy becomes your N, right? And if I want to resonate out the imaginary part of this capacitor, what should I do? Should I put a inductor like this? Clearly no, because if I use an inductor like this, L and C will resonate out and our entire I in will go into R. So no division ratio, right? So if parallel is not possible, what other options do I have? Obviously series. So essentially what I need is, so by the way, yeah, so essentially what I will need is something like this. So if since this is R, this will be R by N square, where N is omega RC, correct? If you are paying attention, you should readily understand this. So this is an RLC reciprocal circuit, right? So now if this is R, this is L, this is C, looking from this port I get R by N squared, correct? But you also know that the impedance looking here is R, right? So the impedance looking in this port 2 prime, this 1 prime. So if the impedance looking out into port 2 prime is R, the impedance looking into R into 1 prime is R by N squared. But let's say I use the same network. And do this and say that if the resistance looking here is some R, what will be the resistance looking here? In other words, I am saying that let's say assume the resistance R is connected here. What will be the resistance? I call this now, let's say 1 prime, and this is 2 prime. So what will be the resistance looking into 2 prime? Do you recall this circuit? Of course you recall, because this is basically looking from here, it is having a voltage division across this, and this will basically upconvert the value of the R to a higher value, right, of R times N squared, right? So this will be R, I should say N1 squared, right? This is R times N1 squared, where here this N is omega CR, right? Or did I make a mistake? Yeah, N is omega CR. What is the N here? Here the N1 is omega L by R, right? Or it might call this L1 C1 omega L1 by R, right? So the key thing to note is that the same circuit, depending upon from which port you are looking at, it can upconvert or downconvert a resistance, and that should not be surprising. Just like, I mean, this is a transformer action, isn't it? If it's a transformer action, then I should be able to look at either port of the transformer. If looking from one port I am getting increasing resistance with respect to the other port, then looking for the other port I should be getting a decrease in resistance, right? So that's hardly surprising. So once you know how to go about looking at these circuits, right, you should be now be in a position to come up with these impedance transformers as and when required, based on the requirements that you have. You do not have to be limited by the architectures that I showed you. You can come up with your own architectures, right? All you have to do is to keep in mind that if you want to increase the resistance, you have to step down the voltage at the other port, right? Or if you want to decrease the resistance, you have to step down the current in the other port. Now, how you do it is totally up to you, based on the requirements that you have, right? So far we have been discussing about how to transform one resistance to another based on the analogy of impedance transformation in a transformer, and we have used inductors and capacitors in certain ways to take the resistance from one value to another value and so on, right? So that might give us an impression that regardless of whatever transformation ratio I need, I should be able to transform one resistance to another, which in principle is not incorrect. But the problem in that definition, in that assumption, is that right now we have neglected any loss in the components, right? So for example, with when we were discussing how to make an inductor or a capacitor, we also saw that there is certain amount of losses associated with the inductors and capacitors, right? Which means that these inductors and capacitors, they are not ideal. And individually, you can think of an inductor to be an inductor L having a series resistance Rs, let's say, right? And this we discussed in the previous lecture when we were starting off with the definitions of Q. And what was the definition of Q in this case? We saw that now I am going to distinguish between the definitions of Q. I am going to call this a component Q, right? Because this is associated with one component with an inductor, and this was in this case omega L over Rs, right? And we saw if there's an inductor, if there's a capacitor, if the resistance I'm modeling it as a series or parallel, and these expressions keep on changing, but what doesn't change is the definition. The definition is, the classic definition is 2 pi times energy stored per cycle by all those things. So it reduces to omega naught. So Q at omega naught, I should say, because Q is also a function of omega naught, or Q is a function of omega. If I am evaluating at omega naught, this becomes omega naught times energy stored, or peak energy stored, divided by power dissipated. Right? So now if we are using these L's and the C's, right? So then what we are essentially saying is that if you have a matching network here, and if you have R here and you are trying to deliver power, I know P in is equal to P out only if there is no loss in the matching network. But if there is a loss in the matching network, then P in will not be equal to P out. Right? And what is the source of loss? One way to think about the source of loss is the finite Q factor for your components, right? Your capacitor will have a finite Q factor, your inductor will have a finite Q factor, right? So finite Q factor of components leads to losses in the matching network. So finite Q factors of components leads to losses in the matching network. Okay, so this we understand. The next thing is, next part of this lecture is to estimate what the losses are in terms of the Q factors. Okay, so but before going there, we need to get some of our definitions straight. All right, so let's say let me talk with an example of a parallel RLC network, right? So let's say I have a parallel RLC network. I mean, you can choose any network, but just to make sure that we understand the point that we are trying to make, I'm taking the example of a parallel RLC. Okay, and let's say you are driving it with a current source, right? And at some, I'm not showing the current source, but you can as well show the current source. There's no harm done, right? So, but I'm interested in only the stuff inside the box, correct? So what is the voltage? Let's say once you have driven this, the voltage across the capacitor, and I'm only interested at resonance, right? So I know that at resonance, omega naught, that is resonance, omega naught square is 1 over LC, right? So what does it essentially mean? This means that the omega naught times L, right? I can basically say that omega naught times L is equal to 1 by omega naught times C, right? So impedance offered by the capacitor and the impedance offered by the inductor are identical, right? In other words, I can also say that the amount of energy, peak energy stored in the capacitor is equal to the peak energy stored in the inductor, and they essentially exchange energies, and that's how resonance happens, right? So if you think about it, the voltage across the capacitor at resonance, I can let's say it's something like this, right? And let's say it goes from Vmax to negative Vmax through 0, right? So what will be the current through the capacitor at resonance? By the way, at resonance, this L and C are isolated, right? They are almost, they have their own world and it's not interacting with R at all, correct? So what will be the current through the capacitor? Or even before we go to the current through the capacitor, let's see what is the Q of the tank, right? So if I have to find out the network Q, by definition, what is it? It is basically omega naught times energy stored. And what is the energy stored? Energy stored is energy stored in the capacitor plus the energy stored in the inductor, right? So, and can you comment on, can I get this information out? That is the total energy stored in the tank, omega naught times energy stored by power dissipated. So this energy stored, can I get it from either the inductor or the capacitor, or do I need to have both of them together? Note that both the energy, currents and the voltages in the capacitor, I mean these capacitors, the total energy in the capacitor is in this tank is constant because they are exchanging energy with each other, right? So other way of to think about it is that whenever there is a, for example, if this is your capacitor voltage, what is the capacitor current? So let's say your capacitor voltage waveform is what? VCT is, let's say, V max sine omega naught t. What is the current to the capacitor? ICT is C dV dt, right? So which means C omega naught V max cosine omega naught t. So what will it look like? So one is sine, other is cosine, right? So it should basically look like this. Something like this. And if you see that 0, where will the 0 be? Obviously, wherever there is a maximum voltage, the differential of the voltage is 0. That's essentially the current. So you will have a 0 here, right? Kind of, it's not aligned properly, but you will have a 0 here, right? So, and where is this current coming from? This current is essentially that is the current in the inductor and the current in the capacitors are being exchanged, right? So in other words, I can basically say that if I check the total energy in the tank at any point of time, I'll take the voltage, see, half CV squared for the capacitor voltage and half Li squared for the capacitor, for the inductor current, and add them up. And at resonance, since omega naught L equal to omega naught 1 over omega naught C, if you add up the total energy at any point of time, you are going to get a constant value. So if that is the case, then I can as well define everything at any point of time, or at any convenient point of time where my mathematics becomes easier, right? And naturally the mathematics becomes easier at any point of time where my one of the currents or the voltages becomes 0, right? So in this case, I will rather take maybe I want to take the instance where the current in the inductor is 0 and the voltage in the capacitor. The current in the inductor is same as the current in the capacitor because they are sharing, the currents are flip-flopping between the inductor and the capacitor and not going out, which essentially means that if I take that point where the total current is 0, the entire energy of the tank at all point of time can be found out by the energy of the tank across the capacitor when the voltage is maximum. Okay, that's all we are doing, right? So what is the energy stored? So then I know that Qn is omega naught times half C V max squared. Why? What is the power dissipated? The V max voltage also appears across R, that is the amplitude of the voltage across R, which means the power dissipated in the network is half V max squared by R, right? So this goes, this goes, so you get omega naught RC. This is the Q of the tank, and I also know that omega naught C is equal to 1 over omega naught L. So this is also equal to R by omega naught L, right? Once you come up with an expression, you should always do a sanity check. What does this essentially telling you? It's essentially telling us that as R goes to infinity, the Q becomes infinity, tends to infinity, which means it's an ideal tank. Does that make sense? Clearly it makes sense, because if R goes to infinity, I do not have any loss, right? It's R is in parallel, so if there is no loss, which means I should get infinite Q. So right, so that makes sense. So this one kind of checks out. Okay, fine. So now what were we interested in? We were now interested in finding out what will be the I'll step back now. I'll go back to the point with which we started, about what is the impact of the losses of the component on the overall power delivered to the network, right? So let's do that, right? So now note that I am making a distinction between a component Q and a network Q, right? So when I am saying a network Q, what I am saying is you have a matching network, and you have an R. So your network Q, Qn, omega naught times energy stored in the network, right? Energy stored in the network by power dissipated, total power dissipated, which means that it includes the power dissipated in the matching network plus the power dissipated across the resistor, right? So this is the total power dissipated, right? Or rather, if I say that this is equal to P dis total, and I will make a distinction with this with the component Q, which is omega naught times energy stored in a component divided by power dissipated in the component, correct? So by strictly speaking, this is the definition. Now I am going to make an approximation, and the approximation that I am going to make is, we have tried to make a decent matching network where the losses are not of the order of the losses in the R, or the, now note the difference in nomenclature, right? So loss in R is equal to the power delivered, right? So note that this includes the power delivered to R, right? So this includes the power delivered, right? Even though I'm calling it a loss, just because the Q definition has loss into it. Okay, so the approximation that I'm going to make is, this approximation we'll see in couple of steps from now, but the approximation that we're going to make is P dissipated in the component is much less than P dissipated in the network, that i.e. power delivered is much greater than power lost in components, right? So this is something we'll keep in mind, right? So now let's go back and write out some obvious statements. The first obvious statement is, if this is power in, now the power in is supposed to be equal to power out only when there is no loss in the matching network. But if this is lossy, like more weakly lossy, let me call it weakly lossy, even though this is not a technical term, right? Which means this power loss is much lesser than the power delivered, right? So this is power delivered. So I know that P in is equal to P delivered plus P dissipated in the matching network, right? So P in is P dissipated in the matching network, which means in the components, right? I'll make another assumption that each matching network is made up of an inductor and a capacitor which are resonating, right? So if that is the case, then I can basically find out the loss in one of the components and be done with it, right? Because I can associate the loss with either the inductor or the capacitor and be fine, right? So that's another assumption I'm going to make. So let me also write it down. Assume that the matching network is made up of 1L and 1C, right? So in principle, your matching network can have multiple L's and multiple C's. Then I can break them up into 1L's and 1C's and then put cascades of each other, right? So in principle, I can do that. So if I can do it for 1L and 1C, then I'm good, because then I have a framework to deal with these, right? So that's what we're going to do. Okay, so let's do this. So what is this power dissipated in the component? So power dissipated in the component is, by definition, is equal to omega naught times power stored in the component by Q of the component, right? If I invoke this approximation that power dissipated in the component is much lesser than the power net that delivered to the power delivered, then I can also make the approximation that the entire power dissipated in the component, so this is, I made a mistake here. Omega naught times energy stored in the component, right? Energy energy stored in the component. Let me just call this EC, right? Because we are only talking about energy while storage, so there is no point in writing storage every time. So if powered every time, right? So I can further make the approximation that the total energy stored, this is not an approximation, this is accurate. The total energy that is stored in the network is essentially stored in the components, correct? So I can basically say that this is equal to omega naught times energy stored in the overall network, correct? Because why can I say that? Because if your network is made up of one inductor and one capacitor, then the total energy stored is equal to the total energy stored in the network is equal to the total energy stored in one of the inductors at a peak state, right? Or one of the capacitors at its peak state. So I can basically make that approximation as long as I have one inductor and one capacitor, right? Fine. So if I can do that, then it becomes QC. Till now, no approximation, right? Now I'm going to make the approximation that, so what is omega naught energy stored in the N? So this is essentially, I can say that this is approximately equal to, so we can say that this is approximately equal to, let me write it down separately. First let me write it down in English, then we'll write it down in formula. I can say that, so this is omega naught times En is the energy stored in the network is equal to Q of the network times the energy dissipated in the network times power dissipated, right? Power dissipated in the network, right? So which is, now I'm going to make the approximation that power dissipated in the network is almost equal to the power delivered, right? So this is the approximation why I am assuming power loss in the components, that is P dissipation of the component, is much less than power delivered, correct? So if that is the case, right, if that is the case, then I go back to this equation, right? I go back to this equation and I go back to this equation to the second expression, and I essentially end up with P in 2B is equal to power delivered plus the power dissipated of the component, which is essentially omega naught En by QC, and omega naught En is Qn times power dissipated in the network, right? So this, and power dissipated network is equal to P delivered. So essentially I am getting Qn times P delivered over QC, right? So we essentially means that, so this now becomes straightforward. So this becomes power delivered 1 plus Qn over QC, which means that power delivered is equal to P in by 1 plus Qn over QC. Now, why is this important? This is important because this is basically telling us that, see, if QC is infinite, right, that is, you have ideal elements, no loss in the matching network, then power delivered is equal to P in, right? That makes sense, right? That should be intuitive. But what happens if QC is finite? If QC is finite, then there is a loss. And note that if as much as you try, you will never able to make QC equal to infinite. So there will be a technology limit beyond which you cannot make higher and higher QC. So for a given QC, the power delivered is essentially power input by 1 plus Qn by QC. Now, Qn is in your control because Qn is the quality factor of the network. It depends upon what network topologies that you choose, right? So depending upon topologies that you choose, it looks like there is a handle which you can use to ensure that less amount of power gets lost in the network and more amount of powers get delivered, because ultimately the goal is to deliver as much power as we want. right? So what is the power loss in the network from this expression? So power loss, power dissipated in the component, which is the power loss in the matching network, is essentially P in minus P delivered, right? So which is basically P in 1 minus 1 plus Qn by Qc, which is equal to what power dissipated in the component is P in times Qn over Qc by 1 plus Qn over Qc, correct? Okay, so can you comment on whether you would like to keep the Qn as high as possible or as low as possible for a given Qc? Of course, you would like to keep Qn as low as possible, because if you keep Qn as high as possible, you are going to have a lot of loss, and from this expression you can figure out that if Qn is high, then the denominator is big, which means the ultimate power delivered is low, right? So ultimately, and this also checks out here, because it looks like for small values of Qn over Qc, this can be approximated as Pn times Qn over Qc. This is assuming Qn over Qc is much less than 1, right? So this is anyway the target, but for a given Qn over Qc much less than 1, your power dissipation of the network is directly proportional to the Q factor of the network, right? So when you are making a matching network with a certain components which have a finite QC, you will have to design your network in such a way that the overall network Q is much lesser than the individual component Qs. Now that might be weird to think about, because whatever networks we have done till now using only one L and one C, the component Q seems to be similar to that of the network Q, which makes sense because there is only one L and C and one lossy element. But you will see that in the next lecture I'll talk about a framework where you can see that you can dissociate the component Q and the network Q to some extent, right? Because you can right away see here is that if the component Q is the same as the network Q, right? If the component Q is the same as the network Q, then you can readily lose like half the power, right? So that's probably not something that we would be happy with. By the way, let me correct the statement that I made. 1 minute back I made the statement that component Q is the same as the network Q. No, that's not the case, right? That is, if you have only one inductor and a resistor and nothing else, even for a simplistic network, they are not the same. You can obviously design for networks which have different network Q than the component Q. But having said that, given the plethora of options that you have, you'll have to choose the ones which have lower component Q. Now, why that is why the point that I was trying to make, while I make that incorrect statement, the point that I was trying to make was Q, if you have a single L and a single C networks like the ones that we have talked about till now, then the Q factor is essentially also the impedance transformation ratio, right? In most cases you saw, if you have one L, one L and R, one C and an R, and you are trying to resonate out the imaginary part, the N was essentially either omega naught L by R or 1 over or omega naught CR, which essentially was the Q factor of the network. So your Q factor and the transformation ratio are essentially the same, which means that if you want to have a large impedance transformation ratio, you end up having a large Q of the network. Now, if you have a large Q of the network and you have losses in the components, then naturally this is pointing to the fact that you are going to have a lot of losses. Granted, you might have some impedance transformation, but the amount of loss that you are going to have in the matching network in the process of getting that impedance transformation will make the matching network essentially useless, right? So in the next lecture you will see that we'll talk about a framework briefly, not in very amount of detail, as to how to dissociate these two aspects, right? Okay, so let's stop.